Okay, thanks very much for coming. So I've been chatting to Cristian Bodnar, who's going to talk today, and after we invited him, I realized that he'd actually been an undergraduate here. It's not the reason we invited you, it emerged afterwards. And actually his undergraduate third year project supervisor, John Shapiro, who's here, was my PhD supervisor. So there's some kind of long kind of connection there. It's like you need a transformer, it's so far away. Yeah. Anyway, so Cristian's been working on topology and geometry of machine learning and neural networks, and did his PhD in that area, and is now working in Microsoft research. And he was telling us over lunch that he's working on some interesting big kind of PDA type models of weather prediction and those kind of things at Microsoft. Over to you, Cristian, for the talk. And here's the clicker.
Thank you. Right. Maybe I should do a quick poll first. So how many people are familiar with GNNs from here? Okay, that's more than I expected. Okay, I think for those of you who are not familiar with GNNs, I think this will be the most weird introduction to GNNs you've ever seen. And for those of you who are familiar, it's the most weird perspective on GNNs that you've ever seen, hopefully. But hopefully you'll find it useful as well. So yeah, let's get started. So first, yeah, let me just give you kind of the canonical perspective on GNNs, and I think this is what you would see in a textbook presentation, maybe. And I'm gonna talk here today only about a particular class of graph neural networks, which are very, very simple. But first of all, maybe let me, let's see if I can, oh, this works. Okay, so let me first explain why you would use a graph neural network. So many problems can be represented as graphs. So you have data living on a graph. And to give you an example, for instance, you could have some sort of material, for instance, where each node is an atom, and then you have some kind of bonds between atoms or some sort of proximity relation, like spatial proximity, like if these two atoms are nearby, you put an edge between them or something like that. Or maybe this could be a molecule as well, and you want to predict, for instance, some property of this material, or you want to predict, some property of this molecule. Maybe your graph is a social network where each node is some user, and you have some features associated with each node, with each user, like what does that user like on a social network, and that kind of things. And then maybe you want to predict something about these users, like are they likely to buy something, or are they likely to, I don't know, be friends with another user, and so on. So these are kind of the sort of tasks you typically see with graph neural networks, just to give you some examples. So the more abstract formulation is that, as I was saying, we have a graph, and each of these nodes in the graph will have some features. So basically imagine kind of having a vector living on top of each of these nodes, describing some properties of those nodes. So that's kind of the formal setup. And what graph neural networks do, they learn representations based on this data that's both relational, so you have the graph with some structure and also these features. And the way they do that is by following a message passing approach, or at least the simplest kind of graph neural networks, but most of them fall in this family. So what they would do, like at each node would receive a message from all of its neighbors. So what this message is some function of the neighboring features. So you compute some function of the neighboring features, and you send them to this kind of central node, and this happens from all the neighbors. And then you aggregate all these messages into like one vector. So this is this green vector here. So this is something you receive from all your neighbors. And the way you compute this is by using some kind of neural network. And then you also have the current features of the node, and then you pass them through some what's called an update function, which just merges these two features, so the message from the neighbors plus my current features of this node, and this gives you some new feature vector shown here in orange. And this process will repeat for all the nodes. So you'll do the same for this node, it gets a message from all its neighbors, and you compute new features, and this will have new features. Here I'm just showing a single node for simplicity. And then you keep repeating this process. So this is just one layer, but you could stack as many layers of these as you like. And at the end, you're going to get some representations for each node, which, hopefully better than the representations you start with. And then you can, do things like classify the nodes or classify the whole graph, depends on the task. Or maybe predict some property, as I was saying, and so on. You could do regression and so on. So that's kind of the setup. And actually, most GNNs fall in this kind of family of models. And the only thing that's different between them is how they aggregate these messages and how exactly they're computed and how you do this update function. So you could have different parameterizations here. But that's kind of pretty much the only difference. But the abstract view, general view is this one. Okay, so this is kind of the canonical introduction you would see to graph neural networks. And now I'm going to show you like the more weird version I was mentioning. So the talk revolves around these objects which come from topology / geometry. So you'll find them they're particularly used in algebraic geometry. They're called sheaves or pre-sheaves. So for the purposes of this talk, these are two different objects, but in the context I'm going to talk about today, they're the same thing. So if you see, hear me saying pre-sheaves or sheaves, they're the same thing. So we treat them in the same way, but there are some differences in general. And in particular, I'm going to talk about these objects on graphs. And I'm going to explain to you how these are related to graph neural networks and how they can be used in some sense to understand graph neural networks to some degree. So let me tell you what they are. So when you have a pre-sheaf on a graph, you basically have the following object. So first of all, you have a graph, and you put some stuff on top of this graph. So this is the graph, and then we're going to stack some things on top of it. So what do we have? We have a vector space, this f of v for each node v. So here's one vector space. It's kind of attached to this node v. We have another vector space for the node u, and you have this for all the graphs. Here I'm just showing one edge in the graph. Okay, the next ingredient is a vector space for each edge. So this is this vector space in the middle. These boxes are meant to show 2D vector spaces, but they could be any dimension. And I'm also assuming these vector spaces have an inner product. That's just a technical detail. And finally, there's going to be a linear map between these vector spaces. So whenever node V is incident to edge E, you're going to have a linear map between the respective vector spaces. So you're going to connect this vector space to this vector space via some linear map. So this is just a matrix here, essentially. And this is just a way to label that V is incident on edge E. There's just a way to label this matrix. It's a bit of a weird notation, but that's what mathematicians use. So that's a sheaf, basically, on a graph. It looks like this. So again, a graph with some extra stuff on top. Okay, here's another way to look at this picture. We are performing some sort of translation between two worlds. So on the left side, we have one world, or one object, which is the graph itself. So this is just the graph you saw before, but redrawn differently. So you have two vertices, V and U, and they're incident to an edge E, and you're just going to have an arrow whenever a node is incident to an edge. So we have one arrow going this way and one arrow here. So that's another way to represent the graph. And what we're doing, we're kind of translating this image into something else. So we're mapping from nodes and edges and these incidence relations to vector spaces and linear maps between these vector spaces. So each of these arrows, incidence relation, is mapped to a matrix. Each node is mapped to a vector space. Each edge is mapped to another vector space. So it's just kind of a translation. We map every node to a vector space, and so on. So this is what is kind of what's called the category theory perspective. So we're kind of translating between two different worlds. So why am I showing this perspective? It's because some interesting things happen as we start asking some interesting questions, such as what happens if we replace this kind of world on the left with a completely different object? So now we have a graph here. What happens if we replace it with a group structure, as in kind of in group theory sense? So let me show you. Okay, so same kind of picture as before. The only thing I've changed is the left side. So before we had this kind of graph I was showing initially. Now we have a group, and it's kind of drawn here in an interesting way. So now, kind of before we had this kind of VUE, now we just have a single thing, a star. It's kind of a dummy object in here. And all the interesting things will happen with these arrows. So these describe the group structure. So basically for each group element, each member of our group, we have an arrow like this that just is kind of circular. And we have this kind of bouquet of flowers kind of shape. So for each group element, you have an inverse group element. So to give you an example, in case you're not familiar with groups, maybe you have the group of rotations. So imagine this is like a 90-degree rotation. You rotate something by 90 degrees. This is the inverse transformation. You rotate it kind of 90 degrees, but in the other direction. E is what's called a neutral element. So this is no rotation at all, and so on. And you can have a lot of other group elements, and this I'm just showing 2 of them here. So this is one way to represent the group abstractly. And now if we perform the same kind of translation as before, we map this kind of star. Before it was a node, now it's just this kind of star. We map it to a vector space, right? Before we were mapping nodes to a vector space, now we map this star. And we get one vector space here, in this blue thing, right? And we're gonna map each of these group elements to a matrix. So if this is a rotation by 90 degrees, this will be kind of the corresponding rotation matrix, and so on. So basically we map each kind of transformation to its associated kind of matrix representation of that transformation. And if we actually look at, the kind of actions these matrices can perform on vectors, we're getting something quite interesting. So we have this notion of group actions, where if you have a vector, like here, V, you have this vector V, you can apply this matrix f of g to V, and you rotate V by 90 degrees. So in some sense, f of g acted on V, or we could say g acted on V via this matrix. So these kind of group elements, they act on vectors by kind of transforming them, right? So if this is a 90-degree rotation, it acts on this vector by rotating it by 90 degrees. And in kind of this terminology, where before we had this kind of pre-sheaf on graphs, now we have this pre-sheaf on groups, and this notion of group actions, you can also call it a pre-sheaf action. Now, something quite interesting happens if we go back to our previous picture, and we ask, okay, what's the equivalent of these actions, of these group actions, but on graphs? So instead of actually having actions involving the group, we're going to have actions involving the graph. And we're going to recover something very interesting. So spoiler alert, what we're going to get is message passing. So when you're going to look at what's the equivalent of group actions, but for graphs, it's message passing. And let me show you. So here's a way to define a left action. So basically, know that kind of these arrows are performing the action. So if we take this arrow here and we act on some vector in this vector space, f of v, so we have this kind of incidence relation and we act on the features of node v, we just take the matrix, the corresponding matrix, and we apply it to these features, and we get something in the vector space of E. So essentially we took some features from node v and we transferred them to node E by multiplying by this matrix. So this starts to look a bit like message passing, right? We pass the message from this vector, from this node V to this edge E. But what we could do is also go from this vector space E to U. And if we compose this, we go from V to U. So we pass messages between neighbors. And the way to do that is you can do a right action. So you go kind of against this arrow. So if we have some features at the edge E, so this HE, you can act from the right by this arrow, by using this matrix here. So just multiply, actually in this case we're going to multiply by the transpose of this matrix. So the transpose will kind of send you the other way around. So you apply the transpose matrix and you get some features at node U. So in this way we move features from here, here, and then to here. If you compose these two transformations, you get a message from V to U. So kind of the perspective to summarize all these things is that you could think of message passing on graphs as very similar to the notion of group actions. They're completely analogous in this way. Okay, so what I'm going to talk about next, I think the math will get less hardcore from here and you can relax, is a way to apply this kind of perspective to actually do some interesting things with it. And maybe this is a good time to stop for questions. Any questions so far? Did I go fast through this? No questions? Okay. All right, so I'm gonna talk about this paper that we had at NeurIPS last year with Francesco Di Giovanni. So Francesco is a differential geometer, and there was lots of kind of geometric insights that you're gonna see mainly due to him. With Ben Chamberlain, with Pietro Leo, my former advisor, and with Michael Bronstein. All right. So let me tell you some problems with graph neural networks. So the main problem I'm going to talk about is node classification. So you have some graph, and your graphs, in this case, the nodes have two labels. So you have these kind of orange labels and blue labels, and you want to separate these nodes, right? You want to classify these nodes. In general, you're going to have some unlabeled nodes in the graph as well, although I'm not showing it here. So you might have some nodes for which you don't know the label. And you want to, at sort of test time, you want to predict the label of these kind of nodes that are not labeled by using whatever you have labeled in your graph. So only part of your nodes are labeled. But something interesting that happens in this context is there's a property of graphs called heterophily, or labeled graphs, should I say, that quite influences your capacity to actually classify the nodes, it turns out, in practice. So what is heterophily? Essentially, it's a measure of how heterogeneous your graph is, in the sense of how many edges you have between different labels, so how many of these kind of connections between nodes belonging to different classes. So I'm showing these with dotted lines as a fraction of the total number of edges in your graph. So if a graph has very high heterophily, basically it's kind of like an opposites attract kind of situation. So you have more connections between things with different labels. And something interesting that people noticed is that when you apply kind of some of the most famous graph neural networks that people use, the higher the heterophily, the more your accuracy kind of drops for these GNNs. And in some sense, it's because these models kind of make an assumption that your neighbors will tend to be kind of similar to yourself. So if you're a node, it kind of assumes your neighbors look kind of the same. But these assumptions starts to be broken once this kind of a graph has high heterophily. And many applications have this kind of a property. So for instance, if you do fraud detection, a fraudster is more likely to connect to legitimate users rather than other fraudsters, right? You want to make money by fooling some real users of your application. So they're going to tend to connect to actually your real users. So that's, for instance, a classic example where you have very high heterophily. All right. Now, another problem is that if you're in this message passing paradigm I was describing, it turns out that sometimes for some families of models, the more layers you stack, the smoother the features become. So what do I mean by smoothness? As you kind of move in the graph from one node to another, the representations will vary just slightly. So it won't vary, they will be almost similar in the limit. And that's a problem, because if you actually want to classify these nodes, of course, if they all converge to the same representation, you're not going to be able to pull them apart and classify them because they all look the same. So that's a problem. And what we're going to look at now is how to kind of use this sheaf formalism to maybe understand a bit what's going on in some existent GNNs, and also to kind of fix these kind of problems and improve our performance by kind of alleviating these issues. Okay, so how do we do that? First, let me just show you a very toy model of how this phenomena could be kind of explained. I'm not necessarily saying this is what actually happens in all graph neural networks, but here is kind of a very, very simple kind of graph neural network that is kind of pathologically suffers from these two problems, heterophily and oversmoothing. And actually, it's more like a physical process. It's called heat diffusion. It's described by this partial differential equation. So this is but here is discretized in space. So this delta here is the graph Laplacian matrix. And you're saying the following. So the features at time t will evolve according to this equation. And this is the heat diffusion equation. We can also discretize this in time just to see, maybe to understand a bit better what's going on. So if we discretize with time step 1, it's this equation. So to get the features at time t plus 1, you take the features at time t and then you subtract this. So this is just kind of a discretization of this equation. We can also massage it a bit and it looks a bit like this. But beyond the equation, let me just show you kind of visually what's going on. So if you think of the features of the nodes as some sort of temperature on your graph, you're going to have some cold nodes and some hot nodes. And at time 0, they look like this. And the more you diffuse, so you evolve time, the features evolve. And there's going to be kind of a heat transfer between the cold and kind of hot regions. And they gradually start to balance out and converge to the same temperature. So everything converges to kind of the same temperature, same representation, right? So this is kind of a very classic case of over-smoothing, right? Everything's super smooth, extremely smooth, right? Everything's constant, basically. This is not quite a final iteration, so there is a slight difference in color, you might notice. But it's very close to kind of infinite time, let's say. And everything's kind of very smooth. And another issue is that if your graph is very heterophilic, actually what happens, the most heat transfer will happen in these regions where you have like very cold nodes connected to very hot nodes. So in some sense, if you have like a lot of these heterogeneous edges connecting different kinds of things, they're going to converge to a kind of similar representation faster. So you can also see how these kind of two problems, heterophily and over-smoothing, kind of interact. And okay, why am I mentioning this in relation to GNNs? Actually, if you look at by far the most popular graph neural network, this is the Graph Convolutional Network by Thomas Kiff and Mark Swelling. It has this equation that you see here. So let me just explain it. So you have an adjacency matrix of the graph. This is a degree matrix, so it's just a diagonal matrix with the degrees of the nodes on the diagonal. So this is just normalized adjacency, this matrix. You multiply by the features, and you also use some linear transformation to transform your features here, and you pass everything through non-linearity.
Are you using periodic boundary conditions? Is the edges?
Yes, a good point. Yeah, I forgot to mention. Yeah, there's some invisible connections from here to here. Yeah. Yes. All right. Yeah, so what this essentially does, this actually you can reformulate it as message passing. This is just wrote as kind of in matrix form. But what happens, like for a given node, it's gonna receive a message from all its neighbors that's weighted by kind of the entries in this adjacency matrix. So you're gonna weight by kind of the inverse of the square root of the degree from these things. So you just kind of go at the corresponding element in your adjacency matrix, and that's your weighting for your neighbors in this thing. And then you're going to sum up your messages from your neighbors. So this is kind of the message passing perspective of what this does. And if we actually massage this equation a little bit, actually we see it's kind of a wrapper around heat diffusion. So we recover this discretized form of heat diffusion that we see here in red, but we've just put a linear transformation on top and some non-linearity. But actually you can prove this nonlinearity and weight matrix in certain conditions. It actually doesn't change the dynamics of this process too much. So it's still going to behave qualitatively very much like this pure heat diffusion. So this nonlinearity and weight don't change things too much in certain conditions. In practice, not so much either, but like also with relatively general assumptions, you can prove something like that. All right, so this is kind of showing why this toy model, at least for this kind of GNN, it actually makes sense and it gives you an intuition about why things go wrong. All right, so to fix this using this formalism of Sheaves, what we're going to do is like build another kind of graph convolutional network, but we start from a different equation. So instead of doing this very simple heat diffusion, we're going to do, you guessed it, shift diffusion. So what's changed? The equation is exactly the same. The only difference is that you have this different kind of Laplacian here. So before we had the graph Laplacian, now we have what's called a shift Laplacian. So this is a more general version of the graph Laplacian. The graph Laplacian is a particular case of the shift Laplacian. And how do you get a shift Laplacian? You need to have a shift structure on top of your graph. So for now, I'm going to assume we have one. And later on, I'm going to explain where do we get that structure from. But for now, assume we have a sheaf on top of our graph. So these vector spaces and linear maps I was showing you before. I'm going to explain later where they come from. But assuming we have such a structure, we're going to get a Laplacian matrix, and it's defined as follows. So first difference is that this is a block matrix. So the graph Laplacian is not a block matrix, it's just a normal matrix. But in this case, we get the block matrix, and if the dimensionality of these vector spaces I was showing before is D, then these blocks will be size D by D. And and why is that the case? Well, if you look at the off-diagonal entries, they're going to be these kind of matrix multiplications I was showing you before. So this is just the matrix composition needed to move features from node Z to node U. So this is kind of the matrix you need to multiply features at node Z to get something in the vector space of U. So this Laplacian essentially tells you how to move features from Z to U by following these matrices I was showing you before. And then there's also the diagonal, which has some terms that show up in the definition, so you get a valid Laplacian. And maybe just to see what happens, how do you recover the usual graph Laplacian? So in the usual, let me just go back maybe to the sheaf I was showing you here. Right, so when you have the usual graph Laplacian, you're in a particular case where all these matrices are one-by-one matrices. So these are one-dimensional vector spaces. All these vector spaces are one-dimensional. So just a real line, basically. And all these things are one by one. And in particular, the matrix here is going to be just a scalar. So let's just go and plug that into the formula and let's see what happens. So, right, so this is just a 1 here. This is just a 1, so we have minus 1 times 1, that's minus 1. So here you're just going to have a 1-by-1 block that just has value minus 1. If we look at what we have on the diagonal, we just have a sum over all the neighbors of V, for instance, here. And we're going to have 1 times 1 over all the neighbors. So this is just the degree of this node. So you get the degrees of the nodes on the diagonal, and minus 1s for the off-diagonal entries where you have an edge. So if you have an edge between U and Z, for instance, you're going to have a minus 1 here. And that's the graph Laplacian, the usual graph Laplacian definition that people use. So that's kind of the relationship. Another interesting difference here is now that since these are block matrices, we're going to diffuse, instead of diffusing kind of scalar temperatures, you're going to kind of diffuse a vector. So you have a vector feature at each node. So yellow node has this vector feature, the green node has this vector feature, and when you multiply this matrix by these features, you're going to kind of evolve each column in this matrix separately, and you can have multiple feature channels. So you can have multiple vectors at each of these nodes. So at node V, you can have multiple of these vectors kind of as feature channels. And the way you can see this is kind of a continuous in time message passing GNN. So you could kind of think as layers, discrete layers as being discrete time. In this case, it's kind of like a continuous time, continuous number of layers, and the evolution is kind of described by these things. Yeah, maybe it's a good time to pause for questions. Anything that seems confusing? Quiet audience. Okay. Okay, so before I had this nice picture with like what happens when you do like heat diffusion and these temperatures kind of balance out and so on. But what happens when you do sheaf diffusion? Do you have a nice picture? Not so nice. I have a picture, but it's quite abstract because it's more complicated. So here's what's going on. This is a geometric way to kind of think about what's going on. So in differential geometry, you kind of have manifolds. So this is just showing kind of the upper part of a sphere here. And when you have like a sphere, you can define at each point kind of a tangent space, right? This is kind of all the tangent vectors, tangent at that particular point. So this is what these blue regions are showing. These are your tangent spaces. And now there's this concept in differential geometry. If you take like some vector tangent to the surface at some point, there's a way to kind of move it into another tangent space. And the way you do that is like you take this vector and you move it just slightly in a way that it stays parallel to where it was just before. So kind of try, like, if this is your vector, move it a tiny bit so that it stays parallel to where it was before. Obviously, if you kind of keep doing this over long distances, things will not longer be kind of parallel in the usual sense, right? Like, for instance, this vector here has been moved here. This one is definitely not parallel to this one. But kind of locally, if you kind of move things very slowly, it stays parallel in a local neighborhood. But over long distances, it's not. But because it stays locally, this process is called parallel transport. So why transport? Because you you move vectors from one tangent space to another, and parallel because you kind of try to keep things parallel as much as possible. And how do you move these things? Well, the actual way to move it depends on the kind of curvature of the surface you're doing this on. So you could do this on any surface. But the way you can think about these sheaves and these kind of matrices that I was telling you about that tell you how to move a vector from a vector space to another vector space is kind of a discretization of this manifold. So you kind of have a graph on top of this manifold, like the one showed here, and you have some matrices here that kind of tell you how to move these vectors. So in some sense, what's kind of the point here is that when you have a sheaf structure on your graph, you could think of it as some sort of geometry you put on top of this graph that tells you how to move vectors around. So when you have the usual graph Laplacian, you kind of have a trivial geometry where moving things is kind of trivial. And now you kind of need to multiply by these more interesting matrices to move things around, rather than just multiplying by 1 as before. So yeah, basically these kind of messages between nodes are kind of also analogous to kind of how you do parallel transport in differential geometry. And when you do diffusion, you're kind of evolving all these vectors at all these locations in each tangent space. It's kind of like diffusing a vector field over the manifold. As I said, it's still quite abstract because it's a more complicated process. So it's not as easy to show. But you could think of it as a more general diffusion process. Yeah, and this is the point I already made. Like, it's kind of what we're doing here now. So just to get a bigger picture, if this all seems confusing, the bigger picture is we now put some geometry on top of our graph. And now when we do diffusion, something more interesting happens. So we're not going to have this boring heat diffusion we saw before. The process will behave quite differently. Yeah, I think thinking has a question.
Yeah. So I just want to confirm one thing. So when we talk about moving on a manifold from one point to the other, we usually talk about the shortest path, right? Because of the metric, we have a shortest path defined. But then when we connect this with a graph, where the shortest path comes from?
Yeah, so you're right. Like when you move along the shortest path called geodesics, in a graph, like all your basically shortest path to your neighbor is the edge to your neighbor, essentially.
Okay. So this shortest path is defined just based on the discrete neighborhood.
Yeah, exactly. Yeah. So your graph connectivity gives you kind of the shortest path. Yeah. Yeah, so that's the big picture. We have a more complicated geometry on our graph. We do diffusion, and at the end, hopefully something better happens this time, because otherwise it was wasted time. And here is an example with an actual diffusion process. So this is time 0. We have a graph, and it's labeled. Different colors mean different labels for these nodes. And the features of the nodes are the position of the nodes in this box. So basically, I don't know if this is 0, 0 or something like that. These nodes here have features close to the 0 vector or something like that. So basically, it's just 2-dimensional features, and the position is the actual feature of the node. So that's just a way to visualize the features. And at the end, you can see this graph is just scrambled eggs. So like it's very hard to disentangle the classes, right? Or it looks hard at least, because everything's kind of messy. There's no kind of immediate pattern. There's nothing you can kind of separate nicely, at least not visually. But if you have some nice geometry on top of this graph, so we have some sheaf structure, which I'm not showing here, because it's kind of impossible to visualize on so many nodes. Well, we have some sheaf structure, and now we do this diffusion process, and we evolve the features. So what does that mean? It means the position of these nodes will change. So remember, position is the actual feature of the node. So as features evolve, these nodes move around. And you can see as we evolve time, these nodes kind of start to cluster nicely, and in the kind of limit, we have some very nice kind of separation of all these nodes. And from here, you can just visually classify them. It's very easy, right? You can just draw a line here, and you separate this orange class from the other classes, and so on. So it's very easy to do like a linear classification at the end. So if you have the right kind of geometry on top of this graph and you do diffusion, you can separate the classes. So that's kind of the intuition why we bother to do all this shift stuff. And we have a result showing that you can actually do this in general. So this theorem says that for any node classification task that you might have on a connected graph, although you can say something about more general graphs, but on a connected graph, there exists a sheaf, so there exists a geometry such that if you perform diffusion for an infinitely long time, at the end you're going to get nicely separated classes like this. So basically for any problem you have, there's always some geometry that will solve the task for you. And I should add here for almost any initial conditions, so it doesn't work quite for everything. But like,
what about the dimensions? So in this case, it's two-dimensional.
Yeah. So you.
Vector. So
yeah.
In this theorem, what's the?
Yeah.
Could it have to be very high dimensional and difficult?
Yeah, that's a good question. So basically, the more classes you have, the more dimensions you need. Yeah, we have more granular kind of results about this. I think this is kind of more like 5 or 6 results, but it's kind of the shortest version if you want. But yeah, like that's a good question. You need to increase dimension to prove this for arbitrary number of classes. So you would have a dimension that depends on the number of classes. But yeah, so what's kind of the nice thing about this is that if we have a problem, we know there is a sheaf, so we could aim to find it. So that's kind of the caveat here. You don't know what this sheaf is, right? No one gives it to you, because then it's problem solved, right? But then you need to find this geometry to actually solve the task. But it makes sense to try to find it because there exists one. So that's kind of the gist of the theorem. But it doesn't mean it's job done, So how do we find it? So what we're doing is we actually learn the geometry using neural networks. So what we are doing, we're going to have some vector spaces. This is something you define beforehand. So I'm going to say beforehand, all my vector spaces in this case are two-dimensional. So that's a hyperparameter. I'm going to say beforehand that's the case. The only thing that's missing then is these matrices. So we need some matrices here. And there's a very easy way to do that. Each of these nodes, so node V has some features XV, node U has some features XU, so this is kind of the problem definition. And we can use these features to actually learn these matrices. So we pass through some neural network, the features of node V, the features of node U, and we get the matrix. So this is a matrix-valued neural network, and it gives you a matrix. And to get the other matrix, you just apply the same features, but in reverse. So first you supply the features of node V and of node U, and then of node V, and then you get a matrix here. So now you have everything you need. You have the definition of the Laplacian. You just need to plug in these matrices into the definition, and you have your diffusion process, and you're done. And the way we learn these things, we train the model to classify the nodes, and we backpropagate through everything. And that's how you learn this. So we kind of backpropagate through the whole process. So in some sense, what this does is you learn the geometry that helps you most to classify the nodes. So that's kind of what you do via backpropagation. Yeah, so that's kind of the essential idea here. And I want to make maybe a comparison with like graph attention networks, which are kind of also a bit like transformers. Well, transformers are a particular type of graph attention network, but maybe it's useful to see these two equations side by side. So what do you do in a graph attention network? You learn an attention matrix based on the features X, and then you apply these attention matrix to the features. Locally, this looks like this, right? You have some features for node I, for a neighboring node J, and you're going to compute this kind of attention coefficient Ij. So how much attention does node I put on node J? Now what we're doing here is very similar algorithmically. Instead of learning an attention matrix, we learn a sheaf Laplacian matrix. This is more complicated because instead of learning a single scalar here, for each node I and neighbor j, we're going to learn a matrix, which is going to tell us how should we process the features of the neighbor j. So it's a more complicated transformation we're learning, that instead of just a scaling of the neighboring features, we actually learn an entire linear transformation of the neighboring features. So once you learn this Laplacian, you apply it to the feature matrix, so like here. So this is kind of very, very similar to what happens in graph attention, but it's more general in some sense, or more complex. Okay, now let me show you some results of this approach. I'll try to speed up so we have some time for questions. So first we looked at a synthetic example. So here we are looking at maximally heterophilic graph. So this is a bipartite graph. So you have just kind of two classes of nodes, and you only have connections between different classes. So it's just a bipartite graph. And we have some theorems showing if you actually do this weighted graph diffusion. So this is heat diffusion where you weight your neighbors. So it's a bit more flexible than what I showed. We have a result showing if you do diffusion like this, you can't solve this task. And indeed, this is what we see. Like if you diffuse with a model like this, performance actually gets worse than initialization time. We know here to design an actual optimal geometry. You can find it by hand because it's a particular case. And we have this kind of oracle diffusion with this kind of oracle geometry sheaf. And you can see performance jumps to 100% and it stays there, obviously, because it's like a perfect scenario. But if you try to learn it, actually you can see that the model manages to get close to 100% accuracy on this toy example by just learning the geometry on its own, so without being told what the right solution is. And actually, if you look at how the off-diagonal entries these transport maps. So here we just did in dimension 1 to keep things simple. And if you look at the coefficients, you multiply. So basically, if you look at these matrices, which are 1 by 1 in this case, so they are scalars. If you look at these scalars, you're going to see they're all pretty much, the model learned to have negative scalars. And this actually makes sense. So this is actually what this ideal solution is based on. You can show when you have these negative kind of signs along all edges, what the diffusion does, it polarizes the two classes. So it kind of pulls them apart. And you can show this analytically. So kind of the essential thing from here is that the model learns something sensible. So it actually learns something pretty close to the ideal example that we used at the top. It also has like a peak around 0. So if you learn a 0 for a certain edge, you basically prune that edge. That's also kind of a valid solution. You can prune a few edges. It's not going to influence your result. So the model did actually something super sensible. So I should have said, in orange, these are these numbers after training, and with blue is just at before training when everything's kind of randomly initialized. So the model did something sensible. And we also looked at some more real-world graphs with various heterophily levels. So more heterophilic graphs are on the left side, and they get less heterophilic as you move to the right. And we have kind of multiple versions of our model, so these are shown here, where depending on the kind of matrix we learn, so for these transport matrices, you could learn diagonal ones, which is a bit more easier because you need to learn fewer numbers basically. They could be orthogonal, or you could just learn an arbitrary general matrix. So we have these three versions. In general, these orthogonal matrices work better, maybe also as a kind of regularization here. Since you have constraints on orthogonal matrices, you have fewer parameters. These are colors. So red are kind of top score, blue is second highest, purple is third highest score. And this outperforms actually many of these GNNs that have been designed specifically for these heterophilic and over-smoothing tasks. And actually also this solution that we derived here via Sheaves, actually many of these baselines, actually they do this. They learn some negative numbers. They manually put some negative transport maps in there, so they initialize all these things with -1s. But it was never kind of explained in these papers why that actually works, or why it was more like kind of an intuitive explanation. But we kind of recovered some of these things that other methods have been doing, maybe in less principled way or more like guessing. And this kind of shift perspective kind of helped explain why that actually makes sense. But we also show there's actually many more solutions if you go in dimensions above 1. So actually these results here, they go in dimensions up to 8 for these vector spaces. So there's way more solutions as you go high in dimensions. So they only discovered a particular solution in dimension 1, essentially, what these papers were doing. All right, I think I'm going to skip this next section maybe just to have time for questions. And if there's no questions, then I can come back to this. But yeah, these are some follow-up shift neural network works done by students I worked with. And yeah, thanks for your attention. Yeah, are there any questions?
All right. Questions? Yeah.
So these transport matrices that you learn, can you enforce some kind of symmetry in those? Like if you know that your data has a certain symmetry, can you make use of that by putting that into the transport matrices?
Yeah, you can totally do that. Yeah, so in some sense, this is what we kind of tried to do. Like, although we didn't do any kind of symmetry constraints in here, but like this, for instance, we constrain these matrices to be orthogonal. But you could put other kind of constraints on them. You could say, yeah, it's a symmetric matrix. I guess the diagonal matrix are also symmetric. So yeah, but we haven't looked at that in particular. But yeah, it's easy to do. You would just learn the lower triangular part and mirror it or something like that.
I don't mean like a symmetric matrix. I mean like if you know there's a certain symmetry between like the nodes of your graph, like for like physics application. For example, if you know that momentum is conserved in your system, and you don't put it in the data, but it is just the case. Can
right.
You somehow.
Oh, you mean in that sense? More like, I mean, yeah, I think you can probably do it. I haven't looked at that. But yeah, I guess you would look at this kind of equivariance and things like this, and I guess you could derive some equations on how these things should behave if you want, you know, these things to respect this symmetry. So I think I don't see anything stopping you from that. I think so. Yeah, sure. Good question.
Okay.
Hi, thanks for the talk. I'm curious about the scaling in this, because I don't work with one-dimensional data almost ever, so it seems difficult to me for me to imagine sort of how broadly applicable this is to sort of like wide encoding of
yeah. Yeah, so actually the nice thing with this is that they scale pretty much same as regular message passing GNNs. I should maybe explain something better. Right, let me go back to this picture here. So this kind of dimensionality for these vector spaces should not be confounded with kind of the dimensionality of the features. So if you actually have, if your features are high dimensional, you're just going to use a ton of feature channels here. So it doesn't stop you from actually having very big vectors with a ton of features. Actually, for all these benchmarks I'm showing, features are about 1,000 dimensions or something like that. So here you would just kind of need to package your features into these kind of d-dimensional vectors, but you could have as many as you want for these things. So that doesn't restrict you. So this kind of should be the number of feature channels, and the dimensionality of these vector spaces should be decoupled. Basically, there are two different hyperparameters. And it's true that in the dimensionality of the vector spaces, so kind of in this dimension, you scale less well. I think if I remember correctly, we have an analysis in the paper, but I think it's kind of like quadratic in that dimension, potentially cubed, I can't remember. But that dimension is always kind of small. So in our case, we tried up to 8 or something like that. But in this dimension of feature channels, things stay linearly. So actually it scales nicely, assuming you kind of treat this dimensionality as a constant of these vector spaces. Yeah, then everything kind of scales nicely. Also in usual GNNs, this kind of dimension is 1 essentially. So they kind of work in these one-dimensional tangent spaces, if you want, or like kind of yeah, vector space.
Cool. Thank you.
Yeah.
At the back. Yeah.
Yeah. So thank you for your talk. My question was about the geometry induced by the sheaves, because it looks like the geometry induced. A good geometry should have some sort of relationship with the geometry of the data or the topology of the graph. Mm-hmm. So I was wondering if there is a theoretical connection between the two, or there is something.
Yeah, so I think, yeah, you're right. So it would depend on two things. One is like, what are your features essentially, and what your graph looks like. So these are the, because that's gonna influence then pure diffusion process, right? And both of these are kind of taken into account in our method. So when, let me just go back to this slide. Right, so obviously we learn these matrices based on the features, so these will be taken into account. But to learn this, we only use these kind of local features. So at node V and node U, we don't use other features that are further apart to learn this. Although we have, in practice, what we do is like we also have like a more general model that learns a sheaf at each layer in conjunction with message passing. So as you do more runs of message passing, you gather information from bigger regions. So then even if you use just these features will be a function of bigger neighborhoods. So you actually take bigger neighborhoods and even the graph structure into account as you learn these sheaves at kind of deeper layers. So that's kind of how these elements come into the picture.
So if I can have a quick follow-up on this. Say that you know already that your topology on the graph has a certain homology, or the manifold of your data has a certain whatever, like topological properties of it. So can you say something like mathematically about the geometry induced by the sheaves moving this information, or is it like everything there?
Yeah, I don't know if, yeah, I think in general, like probably such abstract mathematical properties of the graph probably will not be super important for the classification task unless they are related to it somehow. So, but in general, I think it's very, very hard to make that kind of statement. Also, like to kind of analyze these things by hand, for instance, it was only possible in that bipartite graph setting where, it was kind of clear what the ideal solution looks like. But if someone gives you a graph with 1 million nodes and all sorts of features, like if someone gives you the Facebook graph, I have no idea what's the right sheaf for that, right? Like, and that's why we learn things. Like, it's very hard to say manually. Like, yeah, maybe more work can be done to at least say high level how the sheaf should look like. Maybe some high level properties, but it's hard to write things in more detail.
Yeah, the row in front, yeah.
Yeah, just word on that comment. I felt like the model is learning a field equation, sort of. So sort of like matter tells space-time how to move. But that's not my question. How to curve. But that's not my question. My question is, you talked about high dimensionality. Have you tried playing around with rotations of these symmetry groups that could maybe take it to representations of multimodal data? So in a form so as to sort of play around with social networks and knowledge or something like that, text or video or images or something.
Yeah, we haven't looked at any multimodal stuff. I think it's also probably related to the previous question about symmetries and things like that. Yeah, we haven't. I think an interesting avenue to explore, and I think some people are looking at that, are graphs embedded in 3D. So like if you have molecules, proteins, that kind of thing, then you need to respect some symmetries, and then it's interesting how do you adapt these diffusion processes to respect these symmetries. And then maybe also kind of finding some analytical nice results about these things. So I think that's kind of an area where I think something like that would be interesting, but I haven't explored.
Yeah.
Two quick questions. Firstly, what is the computational complexity of this in terms of the dimensions of the vector space itself?
Yeah, so I don't remember exactly. I think it's d squared or d cubed, something like that. But you can assume d is a small constant, essentially.
Where d, so it's irrespective of the number of dimensions of the vector space itself?
Sorry, say it again.
In terms of the number of dimensions of the vector space. So, for example, in the table you consider d to be 1, right? So the dimensionality of these spaces.
Yeah, so that's what d is the dimensionality.
Okay.
Yeah.
And so, would these models benefit with sort of structural position as well, both structural and positional information in the graph? Or is it just structural?
Well, I mean, I think with any GNN, like if you augment it with more advanced positional features, in general, they would do better. but we haven't really looked at that. Like it's something you can, basically here you can always augment your initial features with some additional positional encodings and things like that. Although we did in some follow-up work something interesting. So former student of mine, it's going to appear at this workshop at NeurIPS, where we look at using the Sheaf Laplacian to compute positional encodings for graphs and like transformers and so on, with relatively promising results. So yeah, that you could use these kind of things to derive some new kinds of positional encodings than the ones people typically use, which are based on the usual Laplacian.
Okay, any more questions? No? Okay, let's thank Chris once more.